All right. So
can you just go back to an example of the branch? You had that one, but had the last one that I just would like you to go through.
okay.
That is not branch, right?
Oh, you mean when I was in that other example?
Yes.
Yeah.
You haven't done any branch.
No, I used an example from the book. I walked through it.
That one.
Yeah.
That one. Where is it?
Yeah, like one of these.
Yeah, I think it's the last one.
This one? This one?
Next one.
Well, I mean, it's the same, pretty much the same code.
Because they have 2 counts there. I just would like to know if that is gonna take.
Well, there's only one. This is the label.
Correct.
This is the destination of a branch.
Correct.
This is part of a branch instruction, where the last parameter is where to branch to if these two guys are not equal.
Okay, and if we had 2 labels, how that would
2 labels where?
on the code, like 2.
Oh, if I had like another label after this, like 2.
Yeah, with 2 lines, for example, how that would work would just
Steal this.
With 2 commands in it.
Yes, 2 labels with 2 commands. Correct.
All right, so you want to have a second label here,
Right.
like 2, and have this guy be, add T3, T2, T1, something like that. And then have this guy be like a branch if equals T2.
It's BEQ.
Ay, 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 ay. T2, T3. This is branch if not equal. This is branch if equal. Like that. So let's assume T1 and T2 were equal to each other. So let's say they're both 5. We'd ask this question. They are equal to each other, so we will not jump there because we only jump to here if they are not equal. So they are equal, so what do? Just go to the next line. Next line, we're going to go ahead and add a 7 to T3. Let's say they were all 5. So let's say now a T3 is at 12. Then we say branch if equal 5 and 12. So we won't jump there. So we naturally go to this line next. And then we naturally go to this line next. So we'll hit every single line.
Okay.
That's that comment about the labels themselves. A label in and of itself doesn't say to do anything. So only if we arrive at it, only when a label is the destination of a branch do we kind of navigate through our program more than just the next line. But if we just stumble upon a label, if I just hit this line of code naturally, this doesn't tell me to do anything special. This is just labeling this line as being associated with this value so that branch instructions that tell you to go there can get you there. Keep in mind, you can also have multiple instructions that all branch to the same place. So I'm allowed to have a label here that never gets called. I can still hit this line of code, right? I can naturally just get to this line of code just by getting to the next thing. But I don't actually have any instructions here whose destination is that. That's legal. You might ask, well, why do you have that as a label? Maybe it's the beginning of a function or something like that, and code someplace else might branch to it or something like that.
Okay, that makes sense.
Okay. All right. So we want to, let's see, we're loading into T1 a what was here. I actually want to do I'm going to move that 7, make this back to a 0. Let's make a little bit, so because typically your registers are all 0 and your memory is zeroed out when you first start. So let's write somewhat of a legit program. So we're going to load into, well, let's actually do this. So we're going to add T1. Let's actually do an add I. So add I, T, we're going to store into T1 the current value of T2. Actually, I'm going to do the current value of 0 and 5. Something like that.
About the 0 thing, so is it normal for, like, should that always be 0?
Most architectures have a 0 register
Okay.
that you can just rely on being 0, the value 0.
So if you tried to change it, would you be able to change it, or is
Most architecture would probably protect against it.
okay? But like for ours, you would be.
Well, yeah, for ours, yeah, we're not protecting anything. That just happens to be a registered name 0 for no good reason. All right. So this is a way of like getting a 5 put into this variable. So I'm going to say I want to add an immediate 5 to the value of my 0 register, which I know will always be 0. So this is equivalent to just saying, go ahead and put a 5 into T1. That makes sense?
Yeah.
Then I can add 15 to T1, storing that in T2, which should give me a 20. And then I can, so would that be a 25 then in the last one? If I run this, there's my 5, there's my 20, there's my 25. So that's kind of the cadence of a assembly language. If you need to start loading in some variables, this is basically like me saying int T1 is equal to 5. That's what that line accomplishes, right? And I get that, I accomplish that using an add immediate off of a known value. I know the 0 register will give me a 0. Okay? So we're going to go ahead and create this. So we're going to say add I T1 0 5. Let's do T2 0 5. Then what we're going to do is we're going to go ahead and do a branch if equal. So BEQ. So we're going to say if T1 and T2 are equal to each other, we want to branch to another place. And let's say that other place is, we'll call it test 1. Let's actually use uppercase, just to kind of match the book's naming convention. The labels have an uppercase letter. They don't have to, but typically they can't start with a number. They usually have to start with a letter. Can't have spaces. Probably can have underscores or dashes. Those are usually allowed, but definitely no spaces and definitely not starting with a number. So whatever it is for MIPS, but that's got to be pretty close to what the architecture is. All right, so if these guys are equal to each other, we're going to branch to test 1. All right. Now I'll just go ahead and leave this add T3, T1, T2. So T3 should have a 10 in it if we hit this line. That's going to be our kind of a test case, right? Because as it is right now, we should, T1 and T2 are both equal to each other. They're both 5s. So if I go ahead and I put a test 1, and then I have a Um, what do I want to do in test one? Let's just do a add I T3 T1 30. All right, so I've labeled this guy test one. My intention is that this instruction should branch to another place in my program when these two guys are equal to each other. What place? The test one place. So since 5 and 5 are equal, I should skip that line and come down to this line. That make sense? All right. So in order for us to say this program executed correctly, you know what? I'm actually going to do this. I'm going to say, just so we can see the both and thing work when we get to it, I'm going to say T4 is going to be equal to T1 plus 30. So T3, if we skip this, T3 should still be a 0. Right? If we, sorry, go ahead. Probably. Yeah. All right, so store 5s into both of those. Then we'll ask the question, branch if they're equal. So 5 and 5 are equal. So we will branch to test 1, skipping this line. This line will not happen, as it should not happen if we write this correctly. So what we'll do is we'll just drop down to test 1, this label. So we will have to search through our program for the label called test 1. Make sense? And what will we do? Test 1 says add I T4 plus, well, put into T4 whatever's currently in T1 plus 30, which should give me a 35. Then the program is done. So if this thing works, when we look at our output, we should see T1 is 5, T2 is 5, and T4 is 35. T3 should still be 0 because we did not execute this line. That's if our branch of equals works. Make sense?
If it doesn't work.
Well, if it doesn't work, then
10 and T4 would still be 30.
Correct. All right, so let's implement a branch of equals. So I'll just steal this chunk here. So branch if equals, if the car of my instruction is branch if equals, then we need to do a test. So we're going to ask a question here. So I want to check the catter and the CADDR, and these guys should both be what kind of values? Names of registers, right? Branch if equals takes in 3 parameters. A register, and a label to go to. All right? So this guy is a register. So let me just dump this stuff here. So CADR of instruction will be the name of a register. How do I get a value out of the name of a register?
Get register value.
Yep, so get just copy this here. So I'm going to say get reg value. Is it like that?
Yeah.
Get reg value of the catter of instruction. That will get me a value. I want to see, is that value equal? So if, now we know we store numbers in there, right? So we can use a single equal sign for numeric testing. EQ would work as well. It's not going to hurt anything, but we know it's numbers. So if equal this guy and just copy this. that guy. So branch if equals says, if these two guys are equal to each other, what are we supposed to do? We're supposed to go to another place in our program. That make sense? All right. So I need to go and find the next instruction to execute in my program. That's what it says to do, correct? All right. So how do we do that? I need to start from the beginning of my program. Is it possible? Let me scroll down here. Is it possible for me to be sitting at an instruction, just for the sake of argument, I'm going to label that guy test 2. Could I have a branch if, just steal it just to keep it convenient. Is that legal code? Yeah. I can have a branch if equals instruction down here that technically branches to a place higher up in my code. That's how loops work. That's how loops will work, right? So that's allowed. So when I do need to branch somewhere, that's effectively what I'm saying up here, right? This right here says if they are equal, and I'm currently doing a branch if equal thing, I need to go to a new place. And where is that new place going to be? Well, it's going to start with my original instructions, but the first line where that label is. So I need to first find that label in my instructions. So we can go ahead and write a little, here, we'll name the function in here. We're going to go ahead and say, we're going to call MIPSI CPU, passing it a program. But now the program we want to pass it is the program whose very first line is the line with that label. So that means I need to pass it a modified version of my program that has started at the beginning of the program and jumped past anything that's not that label until I finally got to that label. That make sense? So if from here, and let me just throw, here, I'll actually throw test 2 here. So let's say we just executed this line, and T1 and T2 were equal to each other. Then we're saying we need to branch to test 2. And when we branch to test 2, what are we doing? We're actually going to tell our CPU to start a program. What program? This program, but starting from that line right there. That make sense? So I need to have a helper function that will go through my original program and start ignoring lines until I get to my label. And then do what? Then pass it the cdr. The program from that point forward. Okay? So we're going to say MIPSI CPU. And we're just going to make up a program here. We're going to say, let's call this guy MIPSI find label of my prog. All right, so we're going to call MIPSI CPU on the resulting program by calling MIPSI find label on a program. I am making the presumption here that globally my assembly code is always stored inside this variable called myprog, just because of the nature of what we're solving here. So I'll go ahead and define something called MIPSI find label. This guy will take in, he'll be a lambda. that takes a program as a parameter and his job as well as a label. So I am going to have to pass it the label. So just before so I'm going to pass it the program, and then I also need to pass it the label, which is the CADDDR of instruction. That is this is the CADDR, this is the CADDR, this is the CADDDR. Okay, so that's the name of my label. So I'm going to be calling MIPSI CPU on a new program. What program? The program returned by MIPSI find label, passing it my original program. And passing it the CADDR, the name of the label I'm searching for. Make sense? Okay. So now we go and write this guy. And for this, I'm just going to go through program and return prog when its car of its car is my label. If car of prog EQ label, if those guys are equal to each other, then I'm in the right place. Else, I need to hop past this line, passing it cdr of prog and the same label I'm looking for. So MIPSI find label will take in a computer program, and the label we're looking for, it'll look at the car of the car, because remember our program is a list of instructions where each instruction is a list. So it'll take the first list, the first instruction, and look at the car of that. And if that matches my label, this is the correct first line. And if this is the correct first line, I don't want to change it at all, there's my program. If it's not the correct first line, I'll call MIPSI find label again, passing it everything but that first line and the same label I'm searching for. And then the MIPSI CPU, what does it do? It runs a program into your out of instructions. So notice that I'm not calling execute instruction by itself. I'm not calling it directly. I'm indirectly calling execute instruction again by asking my CPU to pick up from a certain label. Right? That makes sense? All right, so let's go back to what I had here just to simplify this, because I was showing you, we'll give it more complex examples in a second, but let's get back to this. So as it stands right now, if I had T2 is 5 as well, right? So T1, T2 are both 5. If they're equal to each other, jump to test 1. Test 1 says set T4 equal to 5 plus 30, which is 35. So we will not have changed T3 in this case. T3 should still be a 0 if this guy works. Expected 2 answers but found 2 parts. What are you upset with? Curly braces or parentheses in the wrong place, I'm sure. All right, so if that's the first register value, that's my second register value. If those guys are equal to each other, what do? I call MIPSI CPU on the result of find label of my original program, passing it the car of the cdr of that guy. If it's not, if it's not, then what do? We actually do Nothing.
Yeah.
Yeah, so we just have to have the else. So how do we want to represent nothing? Yeah, I think for our
You have to do something.
yeah. Well, you could anything we do as long as we're not changing our. I mean, yeah, we could. Yeah, that's what I'm thinking. Just do a false in there that we did not take the branch. It will not have had a modification on our memory or our.
Register.
Yeah, well, our registers or our memory. Yeah. All questions were false. All right, so I must have a missing. So that guy ended there for a moment.
Because equal.
Well, that's what I'm checking. So what was so I had BEQ. Okay, good. So this guy definitely ends there. So then we get to this line. That's my question. What do we do if that is true? If the car of instruction is BEQ, then we ask this if. So if those two guys are equal to each other, then we do that stuff. Else, we do that.
Can you find debug?
Well, let's just do this for right now. Because we're going to need an else in here anyways.
I'm going to cut it.
Do it one more.
I don't think so. We're in the right place. Else, I'll just spit out the instruction it's trying to execute. And then we have the one more. So this will be our catch-all, because it's right now it's complaining that our cond couldn't get into any of these things. So let's look at what the instruction was when it spit it out. Did it give me an instruction? No, this is my...
Didn't work though.
T1 is 5.
Well, T1 is 5, so it did the first line.
3, okay,
Yeah,
jump.
T3's 10 now and T4's
It-
5.
Yeah. But that's okay, because we know it's executing some of the lines. So T1 is 5, T2 is 5, T3.
PQ didn't run.
So BEQ didn't execute, so we went to test 1. Let me check the output of this. So I'll just leave it like that, it's fine. Let's just see what MIPSy find label gave us for our... Doesn't like the Spence. There we go.
Is that missing correctly? Something? Yeah. I bet it is like we have
If
extra.
that do... There we go.
You have extra.
Yeah. Now it's right. Now it's right. Yeah, so it's never actually getting to the
Yeah.
BEQ. What's going to be funny is I wrote my assembly wrong. That's probably what it ended up being. This is fine. That is fine. Branch if equal T1, T2. All questions were false.
car instruction DE2. Ah. Here.
I just want to see what it's trying to pass in that last time.
Debugging. It doesn't wrong. Add back the else.
Well, I want to see where it crashes.
It doesn't.
Because I should have gotten at least.
Yeah, but it's a thing that it's not
Steam's not gonna run
compiled.
anything though with it.
Well, I mean, my syntax is not incorrect. So it's dying then on the very first. Oh. Okay.
It must be.
Yeah, I get it.
Otherwise. Oh, is it possible there might have an empty disk there?
Well, that's what I'm trying to see, is what was the last thing it tried to do before it died. And actually, what I'm going to do here is I'm going to. I'm going to take out the dump of all my registers and stuff. Okay, so that's where it finally finished. CPU, my prog. This is my prog.
Nothing.
Yeah, so where it's failing. Oh, I know why it's failing. It's working until it gets to this line. And it gets to this line, and it looks at the car, and it sees a test one, and we don't have an instruction called test
You
one.
should have else to deal with
Yeah,
that.
so our else has to deal with an instruction that looks like this, that actually is this instruction.
Yeah, jumps all over the car.
Right, so we'll do this then.
Else kernel
Yeah, we'll call execute instruction on the cutter.
Yeah. I thought about it at the beginning, but I forgot.
Well, they just don't give you a convenient way of seeing the stupid error. That's good.
I also tried to debug, but I don't know how to put the
Well, debug works fine. It just makes you step through 50 steps until you
Yeah,
can finally
it's,
see it.
I don't know how to put the
Don't you have
breakpoint
to say
on.
cutter
so.
instruction or
Yeah.
just saying cutter?
No, cutter instruction. All right, so if I'm in the else, that means we didn't get into any of those other things, so I'll go ahead and do the cutter of my instruction. I think this guy is where I was, well, I can just put it inside the list, what was this called? Register file and data memory. There's our 5, there's our 5. Okay, so T4 did become a 35.
But T3,
Is still 10, and it shouldn't be. Okay, well, now that it's running right, let's see where our logic broke. So we put a 5 and a 5. Then we ask the question, branch to test 1 if they're equal. So that says go to,
I think it's a problem with maybe the CPU.
well, I'm thinking it's this. I want to see what the result of, oh, hold on, we did change something here. I'm not actually calling it now. We just called find label. When I was debugging it before, I didn't call my CPU anymore.
Because MIPC CPU actually it runs all the commands. It doesn't really jump.
Yeah. So what he's talking about is this. My MIPC CPU is actually still in the process of recursively calling the first thing. I'm then just starting up a second CPU to work on my new thing.
Yeah.
With that in mind, what should actually happen if that's the case, add I T4, T1, 30. It's what's actually happening is this line is occurring twice. So we can't use our original program. Instead, we have to remap inside the current program, because down here, where's my CPU? So these are our instructions we're running here. So we begin. We're showing this is the instruction we're about to execute, whatever. So I'm just going to take that off of there for right now. We're executing an instruction. Now, what we should do is if an instruction is a branch instruction, we have to be prepared for the nature of our program to change. So this is actually a good, it is a good error, because this error tells us why CPUs work the way they work. Earlier I mentioned that CPUs have this thing called a program counter that keep track of what is the current line you're working on for your instruction. What we're doing with our CPU right now is we're actually calling our CPU recursively on the footer of our program. So we execute an instruction, then move on to the next instruction, losing the old instructions.
Yeah.
That make sense?
Oh,
We don't want to lose instructions because we might need to go back and do those again if we have a branch. Okay, so we need to change the way we're executing our MIPC CPU, where our MIPC CPU will execute the instruction at bucket program counter. All right, so let me show you what I mean by that. So we're going to have a define MIPC, well, let's just call it define program counter to be 0. When you first start the program, the first line will be the line at bucket 0. All right. So then we're going to have a function called get instruction that will get the instruction from a program counter, bucket program counter. That's what this guy does. Okay. So define MIPC get instruction. This guy will be a lambda. That actually I think would, if we're going to assume our program, well, no, we could take in a program. That way we can be more generic. Okay, so we'll pass it the program that has all the lines, no lines are cut off of this thing. Okay, it has the entire code base. And it will return for us the instruction at position program counter. I think there is a function called like listref or something like that that allows you to like immediately jump to that, but we'll just write the recursive version of this to
Like index or
is that what listref does? Listref in scheme will get me a certain bucket of.
You probably have to look on the document,
Let's just write it.
or you just using the chart.
didn't you read it last class?
Well, maybe. Let me just look up listref real quick.
Might be.
Yeah, listref takes a list and a zero-based bucket. So this guy will return listref of our program and our program counter. So that's what get instruction will do. All right, so if I ask it, let me just test that real quick. So let's get instruction myprog 2. That should give me bucket 0, 1, 2, so the BEQ. Oh, sorry. It only takes one parameter. So by default, it'll give me bucket 0. So that's our add I. If I change my program counter to 2, it'll give me bucket 2, which is the BEQ. Yep. All right. So MIPC get instruction now always retrieves for me the instruction associated with our current program counter. All right, so in my MIPC CPU, I'm not actually going to go through I'll never actually run out of programs. What will happen, I'll never run out of lines in my program in terms of the list being empty. So null prog won't work. Instead, what might happen is we think about our program as being like an array, a collection of instructions. My program counter might be greater than the length of my list, right? So the length of my list is, let's say, 5. The legal buckets are 0 to 4.
Yeah.
So once the program counter equals the length of my list, I'm done. I have no more instructions to. So if equal length prog.
Should we using greater and equal?
I don't think so.
Potentially.
Well, I mean, you can say potentially, but you hope you don't jump to line 7 from line. You shouldn't have to.
Yeah.
Equal and technically greater than equal is a less efficient. You're only asking one question here. Have I walked off my last instruction? You want to say greater than or equal to, which will still be accurate, but we should only walk off our last instruction once, right? We shouldn't get to 3 buckets past our last instruction. So if the length of our program is equal to the program counter, that means we have run out of instructions to execute. Do this. Otherwise, what are we going to do? We are going to execute an instruction,
As a bucket.
passing it. What instruction are we going to execute? We're going to execute our instruction at bucket program counter. So MIPC get instruction.
And counter plus 1.
Prog. So that's the instruction we will execute. Then our natural thing to do will always be to add 1 to our program counter. Set bang program counter equal to plus program counter 1. Execute the next instruction, increment our program counter. That make sense? Now, we're actually going to see that this is going to give us a problem as well.
Because the be equal, you need to find out.
Yeah, so we're going to see it in a second. We're actually going to have to get our instruction first. I'm sorry, we're going to have to update our program counter, then get our instruction for the previous one before we actually call execute instruction. So we need to get the instruction first, then increment program counter, then execute the instruction. That's the order in which those things need to happen. Otherwise, what will occur? If I get the next instruction and I execute it, that's fine. I'm executing the correct instruction. But something in there might change the value of my program counter, like our branch of equals.
Yeah.
And then the very next thing that will happen out here is I'll change it again. So I change it an extra time in that situation. Does that make sense? All right, so our program counter might modify then in, I guess, that situation. Now, one thing we could do is we can say we will not change the program counter in MIPC CPU.
We change it in.
Yeah. We could say that our program counter is completely driven by execute, where execute under normal conditions will always add 1 to it. But every now and then, it might do something different.
Yeah, if it's branch.
But then after we execute the current instruction, what do? We call MIPC CPU on the entire program again. Not on the cooter of it. Because we're not cutting down our list of instructions. The next instruction we execute will always be the instruction associated with the current program counter. But execute instruction might change that program counter. We can expect it to almost always change it by 1, but sometimes it might change it by more than 1. So if we come up here, let's just look at all the things that it does it just by 1, so we can make those changes. So LW, SW, it's kind of a it's gonna suck to do it this way, but
You have to put a lot of.
it technically is the correct way of doing it.
Or we can add another condition. Oh.
LW, where do we want to update our program counter?
In a helper function.
Well, that's fine, but where do we call the helper function?
But actually, if you put like in the set register value, put into.
Well, right. So I could put it in these guys, but I also have to put it in add I, and which shouldn't be the end of the world. I think that's actually okay.
Because
Well, hold on, that one, no, can't do it there either. Oh yeah, we can.
we can put in the set register value because of every single result in the value chain.
Well, I don't know if that's always the case. Because when you do a set DM or set register value, does every single instruction does every single non-branching instruction? That's the real thing. Because the instructions that we have that modify program counter differently than just by 1 are ones that, so like our branch instructions, I think we could see it in here. This would be the easiest way to visualize it.
It's either changing the memory or changing the register. It has to be. Otherwise, that's not.
Yeah. So here's the instruction summary. So if only the branch instructions don't necessarily change registers, this will work. So LW does modify a register. SW actually modifies direct memory, so we'd have to put it in 2 places.
Yeah.
The offsets, that's from the next chapter. Add I changes the register, add changes the register, sub register, mul register, register. Branch if equals does not change a register, but that's okay. It's a branch. That's going to be our special case. not equal special case. SLT
What else?
is, well, that's set less than. That's not a branch, so we're okay there. That will modify a register, but it's okay because it should only increment by 1. Jump to a label. That's also, that's fine. That's a branch. Yeah. So we only need to put it in those 2 places. So our set functions. Set to list value helper. Actually, we only need to do it the one place because we use the same helper for both of them.
If it's in hardware, it has to be 2, but it's in your software.
Right.
You only need 1.
So actually, we could do it in our, we do an append, so we can't do it there. I was going to say we could do it in our null. Just our dying wish is to increment the program counter by 1. In fact, whatever. We'll do a begin here.
Yeah.
And so our begin will append those lists. Well, let's go ahead and change the program counter. So we'll do a set bang program counter plus program counter 1. So that's the first thing we'll do. And then the second thing we'll do is we'll do our append. There, that's after we found our thing. Otherwise, we're still looking. So we can just do it here in this begin. This still does assume that we always find a value that we're updating, so we can't give it bad register names. But what do we do when the car is equal to the name we're looking for? Well, we have found it. We are about to update our file. I will set program counter to 1 bigger than it used to be. You know what? This is still going to be problematic because who calls set to list value helper? It's going to be our guy that's going to have our set bang on it, and he's going to take the result of this. He's expecting the result to be this list, where now the result is going to be a void plus this list.
Oh yeah.
All right, okay.
Unless
We're gonna hack this.
Yeah, we wrap it outside.
No, we can do it inside. So this is very interesting. So we're not going to do it as a begin. What we're going to do is we are going to create a list containing the result of this and containing the result of this append.
Okay.
Right?
Avoid.
And then we're going to, so that's going to be a 2 list, right?
Yeah. Then we code it.
Return the car or the cooter. So, this is ghetto. So what we're doing here is we need to pull off updating our program counter, right? But we've seen the behavior in our code that when we do a set bang, we get a void. Who calls this set to list value helper? It's going to be like this guy right here, this set reg value. So this guy right here, he's the one who actually calls that helper. So he's going to set register file equal to the result of that function call.
Yeah, so you have to.
That result of that function call for us right now will be void followed by the list we want it to be. Make sense? So what I'm going to do is I'm going to build a list.
Remove the void.
Where's my... Yeah. So right here, I'm going to build a list where the first element of the list is going to be that void thing that we don't want. And the second element will be the list that we do want. And then what I'm going to actually return is just the part of that list that we do want.
Mhm.
The car of the cooter,
Okay.
right? Because the cooter is the list containing the list that we want. The car of that will be the list that we want. It's pretty ghetto.
I would rather write a helper function.
Well, but I mean, it works out pretty well. But that's you definitely want to have probably a comment in there. So this is well, I'll just leave it.
But I'm also curious, if you try to append the void to a list, will actually the void not really append?
Yeah, I'm not sure.
I don't know what the void would be in this.
I'm guessing it might give an error because void is nothingness. We just have a visual representation of that nothingness.
Let's see what it will be.
So
I mean, we finish that
Yeah.
important.
let me take this branch if equals thing off here real quick.
You probably should also deleting the, yeah.
And let's just make sure it'll go through natural code. So we're never going to hit a branch if not equals, so we don't have to worry about that special case.
Yeah.
So it should set T1 to 5, T2 to 5, T3 to 10, and then T4 to 35.
Oh my goodness, it's wrong.
5, 5. Yep, okay. So it did all that stuff right.
Yeah,
Okay?
What do we expect?
So now, if we put these labels back, now what we can do is if we do the branch instruction here, we're just going to update the program counter. That's
Okay.
all that guy does is updates the program counter.
Mhm.
So if we're looking at a branch and they're equal to each other, so if that's a true statement, then what are we going to do? We're going to call our find instruction for that, but that guy should now find the program counter for that. So
And then run it.
no, we don't even need to run it. Just set the program counter correctly. Let the CPU run it the next time through.
Yeah, and the next loop it will run the one there. Yeah, true. Just need to.
Okay. So this guy right here says if they're equal to each other, we're going to call MIPSy find label, passing it the entire program and the instruction we're looking for. So we need to update MIPSy find label slightly. Because MIPSy find label is no longer, and what we're going to do is we're going to go ahead and pass this guy a pause for MIPSy find label. So we're going to pass it the program, the instruction, and the first place we're going to look for it is that bucket 0. And what this guy is going to do is he's going to look at the car of the car. If he finds that label, then what he's going to do is he's going to do a set bang program counter.
Equals to pause.
Yep, pause. Else he's going to find MIPSy find label, cooter of program, passing it the same label, and passing it plus pause 1. So after MIPSy find label is done, he should have update program counter to be the position of where that label lives.
Mhm.
Starting his search at bucket 0. Ultimately ending his search at bucket whatever he found it at.
Mhm.
At which point he sets the program counter. And then that's how this guy ends for the branch of equals. He doesn't actually execute any code. His whole job is, if this happened,
Jump.
jump. Otherwise, if it doesn't happen, what do? we do have to increase the program counter by 1. Program counter always goes up by 1. So we do a set bang program counter plus
Well,
program counter 1. So we either update it to the new location or we add 1 to it if we didn't take the branch.
does the CPU really can do that? I think it will actually break.
I think it'll be fine.
It is a label not found.
That's this thing right here. So our code as of right now should do what? 5, 5. Are they equal to each other? Yes, they are. It should skip past this and only set this to
All right.
missing a closing one. And I'll just finish this up real quick and give you guys a stopping point for this. And then for the homework, yeah, there it is. I'll have you do the other branches. The one other branch and the jump. And read the next chapter. This variable is not defined. What did I call it? Oh, I have to call it my prog here. So there's our 5, there's our 5. We do not have our 10, and there's our 35. So now we're jumping based on program counter. And what's really good about this is we actually were forced to make our architecture work the way that actual CPU's architectures work. We had to use a program counter.
And actually implementing jump is very similar.
Yep. All right, so for homework, I do want you to go, and because we need to stay on track, so I do want you to go and do read through and do all the exercises for chapter 3. All right? But now, for your homework, I'll give you this code as a starting point. I want you to go ahead and update this code for branch if not equal, set if less than, and jump. Those 3. So we already wrote branch if equal. So you're going to write branch not equal, set less than, and then our normal jump. Just those 3. Sound fair? And I'm going to give you this as our starting point. So you're still going to have to prove you understand what we did today. All right, so this is going to be write BNE, set LT, and J.
Can we label a label instruction?
You label that's a good question. I don't think, well, at least not in our current MIP CPU could not do that.
Yeah,
The question is, would you ever want to do that? I think no. I don't think you can label a label. I think you can only have one label associated with an instruction.
But I think we can achieve that through not labeling, like triple label or something like that. So it should be achieving.
Yeah, but that's a very specific example. You would basically have to come back and say, this is what I want to accomplish. How do I hack it to make it work?
Yeah.
And then you'd probably have to like jump to one label, jump back to another label, then jump back up to another label. All right, so we're going to call this guy working MIPC CPU-ish. All right, questions, comments, concerns, bribes. So we're going to read all of chapter 3 and do the exercises, and we're going to write those 3 functions in terms of the code I just uploaded to Slack.